Thank you for coming. So we're here for exposing hiding exploitable behaviors using extended differential fuzzing. I know it's a weird name for the talk. It is almost the second time that I'm giving this. The first time was in Black Hat. When I presented it in Black Hat, the idea was to show that the idea worked, but it was not important what I show over there. What I believe is really important is the idea behind of what I found. So for me, the best outcome of this talk would be that you can either use the bools that I show in the past or now. You can either use the ideas that I'm going to share now, or you can either use the tool. But the idea is that it's all about what you can do with this. So we'll be talking a little bit about what this is, who may use it, how you can use it, that's the tricky part, and why you may want to use this. I'll talk a little bit about common fuzzing. One of the things that I like about Hack in the Box is that there are a lot of people doing fuzzing in here, and this is what they're commonly focused on, and that's okay. But there are also other possibilities when it comes to differential fuzzing. Differential is going to mean that you will be comparing stuff to find new vulnerabilities. And the idea on top of the differential fuzzing is the extended differential fuzzing, where we'll try to find even more issues while we are comparing things. So everybody knows that when we're fuzzing something, the idea is that we'll be disclosing things that shouldn't be there. One of my main goals was to show that there were unexpected behaviors in programming languages the first time that I showed this. But the idea is that you can also find weird functionalities when you're fuzzing things, or you may even crash the software and then go for memory corruption bugs and so on. When using extended differential fuzzing, the idea is that you will be able to find even more vulnerabilities, a wider range of issues to try to exploit a wider range of targets. So there are three possibilities when it comes to fuzzing. You're either a security consultant and someone is asking you to fuzz a piece of software. Either you're testing software, and sometimes this is interesting because you can apply differential fuzzing with just one single piece of software. Or you're a developer and you want to see how your software compares to other pieces of software. So there are two ways you can do this. The first time that I started doing this was manually, and it's painful. I was trying manual tests on multiple pieces of software, trying to find differences. This was 5 years ago when I was testing XML and XSLT, which is a programming language related to XML. I found a series of high-risk issues, including things related to numbers, to random functions, to violating the same origin policy, which still works in Safari until now. And that was all done manually. And what I was doing to know that these things were over there was comparing by other pieces of software, because I didn't know if they were over there or not. After I gave the presentation, I realized that I needed something more robust or more complex to try multiple pieces of software at once. So I started working on a framework that was originally meant for JavaScript. The moment that I wrote for JavaScript, I realized this idea is absurd. I don't want to just test one programming language. I want to create a framework because I want to compare different programming languages. And if I'm able to do this, I can scale it to test any kind of software. So I did something in Python, and I started testing this in multiple operating systems to gather a lot of different information, standard output, error, etc., and expose the unexpected behaviors that you could find. So the thing is, the fuzzing process, what we hear all the time in here, in Hack in the Box, is how they generate the input. This is where all the fuzzers focus, or the tools that aid the fuzzers. What's the idea in here? The idea is that you will be generating an input that is going to cause something malicious on a piece of software. That's the main thing about fuzzing. The input is absolutely important and mandatory. What I did is I didn't focus on this. I tried to keep the test cases as simple as possible when it came to the input, to try to see what I could do with the output. Before getting over there, you need to execute the software. So you grab an input, you put it into a piece of software, and then you check the output. The idea is this fuzzer focuses mainly on what can you do with that output. I'll tell a little bit how we're going to do that. So the only way that you can compare information reasonably is with a database. So I have a collection of some certain databases to have an idea of what can you test, what can you do. So I grab a copy of a plain database and I create a sample function that it has nothing in it. It has just the test meta keyword. The test meta keyword will be replaced by the values defined in here. The function, for example, could be, if we're talking about JavaScript, it would be alert. If we're talking about Python, it could be system, doesn't matter. Or it could be a big chunk of an MP3 file, for example, where you can put the test meta characters at the very beginning of the ith tree if that's what you want to fuzz. It's the place where you will be replacing with values. I want to start by showing you 3 different possibilities of basic things that everybody can understand of what are we going to do. I want to show you what happens when we add 2 plus 2, when we add 0.1 plus 0.2 minus 0.3, and then we have a large number plus 1. Once I have all the values stored in the database, this is one way of adding them. You can directly add them in the database if you want. You're going to generate the permutations of how you're going to combine these test cases. In here, we have only 3 test cases, the 3 calculations. The next thing you want to do is to pick a name of how you're going to fuzz, how you're going to name this fuzzing session. Where are you going to test this? The type of input that you're going to be using. You can either use, if anyone saw the talk about fuzzing JavaScript, the input that they were using was probably either in the command line or in the standard input. In here, you can define whatever input you want. In this case, it's file, so it's going to be using a random name for the file. In the case of the JavaScript talk, they were passing the files as parameters because they didn't want to impact the input-output of the system, but as long as you create a RAM disk, you will be fine. You can do this on any operating system, so that's not required. You can also use URLs and try to, for example, if you're trying to fuzz a browser, or the standard input if you're trying to fuzz, for example, a web server or something like that. For this basic demonstration of what are we going to do, I grab, in fact, there are 8 pieces of software. There are 7 in here for the sake of simplicity. And if you can see in all of them, what we're doing here is just say, we're going to print a test case that we defined previously. Depending on the language, we do this differently. There are 6 programming languages in here, plus BC, which is a calculator in Linux. So, why do we want to do this? To automatize the output. So, what I'm going to show you from now on is going to be a combination of 2 things. Either I'm going to show you the outputs of the tool, or I'm going to show examples of how you execute some of the things that are picked by the tool. So, this is one of the outputs. It generates an HTML file with different tables. And this is the most basic output that you're going to see from the tool. This will be listing the results. You just executed something and you want to see what happens. When you're executing something, you have a test case that you're defining, 2 plus 2, that is going to be related to a piece of software. It would have different types of input. In here, since we also have Firefox, that has a URL associated to the type of input. This means that it was hosted on an automatic web server that is created by the fuzzer. I tested this on my Mac, and the output was 4. And that was easy. That's how we start. The very first thing that we want to do is what happens. In here, it was pretty obvious what the output was going to be. But sometimes, as you start progressing, things are not so obvious. Let's move on to the next one. Remember this calculation. This is simple. The problem is, when you're trying to do this floating point arithmetic, sometimes things do not work as we expect them. We know these numbers in the decimal notation. However, when we write this in binary notation, the values are not 0, are close to 0. So this is the most basic thing when we talk about differential testing. Differential testing is you have a set of values and they are different. So this is going to be picked up by this analysis functionality. BC, the calculator almost at the very bottom, had the number 0. That's because it's a calculator, it knows what it does. All the other programming languages say, okay, it's a number 0 plus a lot of zeros, and then the number 5 whatsoever. Depending on the programming languages, it has a better approach to what the real number is. But it's number 0. Another way of seeing the results, we have seen 2 ways of seeing the results. The first one is you just list all the results. The second one is you're just only focusing on the ones that are different. For example, in this functionality, you wouldn't see the 2 plus 2 equal 4 because there is nothing different over there. Let's move on to the next one. As I said in the very beginning, I was curious about JavaScript, and this is one of the very first things that I was analyzing, that this calculation may only affect JavaScript stuff because this is the maximum number for JavaScript. So if you do this, you will find that this is another way of showing things. You're looking for test cases that produces the same standard output. We could have used the previous function, but sometimes this function comes handy to analyze other scenarios. To make it simple, I use it for this one. So the weird thing is that if you add the number 2, then you will get the real number in JavaScript. That border number is a little bit more complicated to calculate for JavaScript. But on the rest of the programming languages or the calculator, that thing seems to work. So, moving on to the real things. When we're talking about common fuzzing, we're talking normally about detecting crashes when we're breaking a piece of software, or hangs. That means that the software keeps executing, it never ends. So, one of the things that I wanted to prove was that even though this is not a common fuzzer, I still was able to detect crashes. There are multiple ways that you can detect this and abuse them. The first one is you can try to attach a debugger and analyze the output to see in which scenarios you can get potential vulnerabilities. In here, Perl is crashing with a certain function, and you can also get the return code -11, which could be associated with a crash. Nevertheless, return codes are not reliable when it comes to fuzzing, but you can use them if you don't want to attach a memory debugger that increases the execution by a certain amount of time. So another possibility, instead of analyzing the output of Valgrind, you could also detect the different return codes by the software. Perl is a case by itself. I just put this in here because it's weird, the amount of different return codes that it has. Sometimes you can even detect weird behaviors of software when you're checking the return codes. Of course, the -11 was the one that we saw before, which is associated with a crash. But depending on the piece of software, if you just have 2 types of return codes and one of them only shows that has been executed 1 time, it would be worth analyzing why it happened. So this is another way of how can you analyze crashes when we're talking about common fuzzing. What I wanted to exemplify, as I said at the very beginning, was that we can execute them to show that we can get those crashes. For example, in Ruby, we can get a segmentation fault by doing that. We can also break the HITB is the PHP that Facebook uses in a number of different ways. PyPy, breaking. Perl, I think this is the one that I show when I show the Valgrind. This is the one that breaks with a -11. Very simple thing. Chakra Core, the JavaScript made by Microsoft. So, I didn't report any of the issues the last time. I didn't do it with the things that I came across right now. So, I don't know if anyone will pick them up. It will be fun. So, the other thing that you could do is to detect hangs. Sometimes the software doesn't terminate. So how do you know that? Because the amount of time that is taken for all these functions, I just put in here some of the rows that I found. This is for Perl. It's taking around 10 seconds. 10 seconds was the timeout for my session, and I decided that 10 seconds was the amount of time that I was going to consider for a piece of software to be terminated and executed. So these functions may be something to analyze in case they are not working as expected. Perhaps the ones that set benchmark are working as expected and they take a lot of time. Or perhaps these are ways to detect things where you can abuse, as we saw in the previous talk, that the guy found a lot of denial of service attacks. This is another way of getting functions that are going to probably cause a denial of service when you're hitting that function. So you can detect the amount of time that is taken if they were killed. Do something about that. Let's talk about differential fuzzing. So the idea about differential fuzzing is that you are comparing two types of outputs. Differential fuzzing started in like 1996. I think this is where they created the first paper. There were a number of papers throughout the year, but so far they haven't released any type of framework to use it on different pieces of software. All the time that they have talked about differential fuzzing has been about just one type of software being analyzed. The first one was about C, and the last one that I remember was presented at Black Hat USA, and it was about cryptographic ciphers. Again, the logic is always the same. You're trying to find different things when you're putting certain type of input. The thing is, what do we mean by output? There are a number of possibilities that haven't been fully explored, and that's that, of course, it's going to be the standard output, but also it could be the standard error. If there are differences in the error, perhaps we're going to do something about that. Sometimes software will try to open network connections, and sometimes other pieces of software will not open those network connections. And that's how you can detect that something is not working as expected. Of course, if you have two browsers, and you're testing two browsers at the same time, and one of them opens a network connection, and the other doesn't, one of them is wrong, probably. Either the test case shouldn't have been open, or the test case should have been open and the other browser cannot handle that type of input. The return codes may show that something is going on when you're testing similar pieces of software, or eventually the time required for the execution. Sometimes the same piece of input by different pieces of software may take significant amount of time that could be checked. Eventually, you can also know if the software was killed or not and do something about that. So, what can you execute to find these kind of things? The first thing would be the different implementations. For example, everybody uses browsers. Everybody knows that there are a lot of browsers in the market. You can use all of them. And they do the same thing. They open a web page. Speaking about browsers, you could try different inputs with the same browser. Sometimes you could use the command line. For browsers, not the best example. Probably for a programming language, that would be better. Or for any type of program that uses something from the command line that is reading over there. A lot of programs uses files, either by the command line when you're referencing a file, when you're opening a file. Eventually, you could also use URLs if they're trying to open a remote resource, or in certain weird scenarios, the standard input. You can also try to compare different versions of the same piece of software. I can imagine that people who test software are trying to see what are the differences between two pieces of software that was made by the same person, but at different periods of time, so you can see what were the difference between those two pieces of software. And eventually, you could try them in different operating systems. And this is even more interesting for me because this is where you see a lot of things that may have not been checked, like the last time that I presented this, there was a company testing one of the biggest softwares in the market, and this company, what it does is looks for vulnerabilities in this software. Since this software is mostly used in Linux, it hasn't been tested in Windows, and it would be amazing the amount of things that you may find when testing a piece of software into different operating systems. Even though the application may not crash in Linux and may give some sort of output, if you execute the same thing in Windows and you get a different output, you may be leading into something and you may get really interesting things. I'll show you how. The first one is when you're testing the standard output. This is the very first thing that we saw at the beginning. We were testing what was the output of 2 plus 2, right? So in here we have 3 different JavaScript parsers. The first one, V8, is made by Google, SpiderMonkey made by Firefox, and Node, which in this case is using V8. So it should behave the same way. In all these cases, we're using the command line input. So this means that, as you can see at the very beginning, we have what we want to execute between quotes. The first one writes the global object. The second one writes the global object. If you tested this, there would be nothing weird about it. The thing is, even though Node is not purely a JavaScript parser, I wanted to see what happened when executing common things. And this is how you can detect that something weird is going on, that in this case it is disclosing the user, the path, the home of the user, the process ID, and a number of things. So you know there is something weird when you have these different outputs. So in here we have different implementations, and we know there is something weird going on because the standard output is changing. This is not the only way to detect in different implementation that something went different. For this talk, I was trying to analyze what happened with certain Java functions. Always random numbers are something interesting, and I was fuzzing this function getSeed into Java parsers. The first column is OpenJDK, the second one is for Oracle. There are different versions there. This one is 8, this one is 9. So in here, for OpenJDK 8, the software is not killed, and it's going to show an exception that is going to run out of memory. However, Oracle, it needs to be killed because it takes a gigantic amount of time and it starts to consume memory until it crashes. So they behave quite differently, and you can know from the get-go that something is going on by analyzing if it was killed or not, or if there was a difference on the standard error. We talk about different implementations. Now let's talk about the same piece of software, but changing the input. This is weird, but Node helps us with this. So the first line shows that we are writing the command console.log and this between parentheses into the file.js, and we're executing that file. The input in here is going to be a file. For the second column, the input is going to be the command line input, and we're going to execute the very same thing. Okay? The first one is going to be an empty dictionary, the second one is going to be this. I have no idea why. But we're talking about the same piece of software in here, and you can detect something just by testing one single piece of software. It didn't crash. You didn't need something else, just one piece of software and checking how the inputs change. I wanted to check a little bit also for this conference how PowerShell behaved. I didn't get too many interesting things in here, but I wanted to share a little bit about, for example, what happens with when you try to list the directory of where you're sitting, right? In here, the idea is that if you execute this, you will get the same output as writing dir. However, you're processing this through PowerShell. The first column, you're using a file. The second column, you're using the standard input. The first column says, listen, this violates the execution policy set by PowerShell and whatever, a red message. It is horrible. Don't do this at home. But this one executes dir. I don't know why. I'm sure there is some reasoning behind this, but it is a different behavior, and you may want to do something about this. Perhaps the next time you don't want to use a file, and you want to use this. So the idea is that there are ways of using the same piece of software in different ways that you can execute things in different ways. Let's move on to different versions. So we talk about different implementations. That means different pieces of software from different companies. We talk about the same piece of software, and now we're talking about the different versions of the same piece of software. Again, Node helps us with this when we're talking about writing the output of this. If you remember, the problem was that when we were using the command line, it was outputting the user and so on, blah, blah, blah. The thing is, in the past, a lot of time ago, it used to output just an empty dictionary, but well, nowadays it shows that thing. So you can see how the same piece of software has changed throughout time. So the possibilities are enormous. Still talking about different versions. Different versions. Oh yeah, because we were talking about Java. This is another random functionality. I really wanted to find something more interesting, but I still want to share that in different versions of Java, you may see a different behavior when it comes to this. So when you're trying to generate a seed for a secure random number, the behavior is going to be different depending if it is OpenJDK or Oracle. You can tell that from the return code that is going to be different, and you can see that something's going on, or it will be more obvious when you're checking the standard error and see that in one case it says, listen, this is going to be removed. In other cases it says, this is not here. Another possibility, which is more annoying when it comes to a practical term of what are you doing, because we normally only see it in one operating system. But if you run multiple virtual machines or something like that, and you want to fuzz and compare what happens in different operating systems, you may get other things, which are interesting as well. In Python, you have a built-in functionality. Oh, by the way, all the things that you're seeing in here are default functionalities from the programming languages or software. CMP compares two objects. The thing about this is that when you're trying to compare two floating point, not a number, values, the result is going to differ depending on the operating system. And this is what happens. So we have three pieces of software, regular Python, PyPy, and Gton. I don't know if you pronounce it like that. And I tested in all these operating systems, and this was the output in all of them. This would be the correct output when comparing two floating point, not a number values, because they shouldn't be equal. It should be the number one. Linux thinks differently. Linux believes that it should be a -1 for some reason, on the same way as PyPy thinks that it's 0, even though it should never be 0 because there is a non-reflexive behavior of not a number. So you can get a really interesting picture when you test a lot of programming languages and pieces of software at the same time. PowerShell, different operating systems. Remember that when I try to execute this thing over here, this horrible red message, of course, it's not going to happen in Linux, because who cares about policies in Linux when you're talking about PowerShell? So again, different operating systems may show you different results. Let's move on to the fun part. When we're talking about extended differential fuzzing, we have talked about how we were using basic inputs, but we were trying different pieces of software, different operating system versions, and whatever. What we will try to see in here is to try to get more vulnerabilities. We found so far certain issues, but it is really easy to detect certain things like, for example, path disclosure. It's really easy to detect in the output that certain pieces of software are going to be showing the path where they're being executed, or the user that has been executing these pieces of software. Eventually, we can also get errors when we're executing software. We see the errors showing all the time, but we may want to do something about that. The code being evaluated, if you're working with programming languages, you may want to know if a certain input is evaluating code, or if a command is being executed. There are different ways if a command can get executed, and you want to know this. Certain pieces of software, open network connection, as I said before, you may want to do something about that when they're being open, or when they are not being open. And eventually, you may want to know when the files are read. So let's go with the basic thing and talk about how files are deleted in Linux, just to exemplify how this may work, because I had to do this because I wasn't sure that things work like this. When you're trying to remove a file that doesn't exist, you get that that file doesn't exist, period. When you create a file that you will try to remove, and the -c is for confirm if it is going to be removed or not, Linux asks, do you want to remove the existing file? Even though we're on the TMP directory, the directory is not being disclosed. This is another output from the tool, the output of trying to get any path disclosure. When I was fuzzing Powershell, I came across that when Powershell requires a confirmation to delete a file, it may disclose where that file is located. It's not a big deal in here. I'm just trying to exemplify that you can easily get this from any type of software, and sometimes you can escalate things when you're getting these pieces of information. So, exemplifying what happens in PowerShell, when you're trying to remove a non-existent file, the very beginning I show you what happened. In here you get like a big error message that says, in the user's directory, there is no such file named non-existent file, and you get the directory where you're sitting. If you do the same thing by creating a file and then trying to remove the existing file, again, you're going to get the directory where you're sitting, and you can get this information. It may be valuable or not. If it is not valuable, you continue with something else. Let's talk about user disclosure. Sometimes when you see a fuzzing talk, you see all or you either don't see any results at all, as that may happen, or you see a very neat result of how something was executed. But the reality is that when you're fuzzing something, sometimes you get a ton of different results that are doing the same thing, and this could be translated into one single test case. In this case, it was the tool is looking for my username fear that is being disclosed in the output. PowerShell, it's when you write the function, when you execute a certain functionality, will try to output a file into my home directory. I would have expected that to be provided by the user, so it doesn't get written over there. So it was a little bit unusual for me to see that over there. How you execute this, when you translate that horrible list, in here you have like 14 rows doing the same thing, which in fact could be translated to this. When you execute start transcript is going to show the username that is executing the PowerShell. So you can get the path, you can get the user, you also can get errors. When I ask people what they do for a living, I try to ask them if they could give me a real example of what they did lately. I believe the same thing happens for fuzzing, and this is my real example. A month ago, I was testing 3 pieces of software, one for Windows, one for Linux, one for OS X. I don't remember why I couldn't execute the OS X file. The Windows file didn't have a config file. I only had the Linux file to be executed. I was planning to do some differential testing, but I only had one piece of software. Still, I executed through the tool, and I got, there is a functionality to look for errors that looks for certain strings. In here, we're looking for the word exception. I came across the word exception in here, and the saxparse exception is related to an XML error. And due to the fuzzer pinpointing this error, I was able to perform an XML entity expansion attack to try to read files from where this was being executed. And this is how fuzzing works in the real world. You may eventually get one hint of what you should do to get the vulnerability. And this piece of software was made in Java, was not crashing. You were never going to get a crash from this tool. But still you can get the exception right in the middle of the logs and do something about it. When I was fuzzing software, I was concerned about the software being capable of executing code. So this introduced the concept of canaries to me. Canaries are special. When they use canaries in the mines, they put a library over there to see if it was dying or not, and that was the indicator that there was a leak of gas or something like that. Canaries in fuzzing can be really, really useful to detect certain behaviors that normally wouldn't be spotted in other ways. In here, I'm introducing, the first line shows that I'm executing eval to print these two strings, canary token and code. And if I see the string canary token code in here, I'm going to print it in the analysis of canary token codes. This means that the code has been evaluated. This is expected. All programming languages have evaluation functions to evaluate code. However, the embeddable type map in this weird function of Perl probably shouldn't be evaluating code, because that's not what it does. It shouldn't be doing that, at least, I believe. And this is how it looks like. When you take that out from the fuzzer tool and you transform it into a real-world example, you can execute code with the privilege of the user that is executing that. So it is possible to detect how code is being evaluated since you're just trying to concatenate two pieces of string. But it would be a little bit more interesting to talk about command execution. Before running the fuzzer, I create a command in all the operating systems called canary file. Whenever you execute canary file on any of my computers, you will get an echo that says canary token command. This verifies that the command is being executed, that it works, and I will be able to detect when that's being executed. It's pretty simple. So the fuzzer also checks that this has been created, so it won't execute if the file is not there, just to be sure that the canary token command is there. So when I did this in PHP, I saw that two different test cases were providing the same output, which is weird because it shouldn't do that. I mean, they're different. One has quotes, the other one doesn't have quotes. At the very beginning, I didn't know what it was. And then I realized, oh, this is the default output of PHP. If you enable all the error messages on the application, you will see that there is a notice over here. I will show you later that notice. Let me give you a very quick example on a demo, on a video, where I will be creating two files. One of them is going to be executed. It will show in a man page. But when we're referencing the second file, I will be executing code. It all happens because PHP transforms undeclared constants into strings. Let me show you. In here we have a PHP info file, and I will be creating a file called index, I believe, where I define a constant name bash that will be executing the command man. Then I will require the functions.php file, which I'll be creating now. This PHP file is going to use the constant bash along with a parameter to execute a command provided by the user. Well, to execute the man page plus the page provided by the user. It will put the output between a couple of tags so it looks coherent. So we will now be calling, we will try to see the logs to see what happens. We'll now call the index file. We'll provide the parameter page to see the man page of ALS. However, if we call the second function, we provide some extra parameters. We may be able to directly execute code using the same functionality. That's because PHP assumes that the constant bash, since it was not present over there, should be a string instead of a constant. Let's go more slowly this time. These are the two files. This is where we define the constant bash. This file uses a second file to try to execute the man page of ls. The problem will happen when people call directly this one, and instead of executing the bash constant, they will be executing the bash string. This is how the man page of ls looks like. You're calling the index file in here. However, if you call the functions.php file, you leave a space and you run that you want to execute a command with bash, because now we're now executing the bash string instead of the bash constant, you can get that information. And you will see this in the logs. PHP notice, use of undefined constant bash, assume bash between quotes. Yes, PHP is aware of this, but yes, PHP is being a horrendous person by doing that, because you're changing the behavior of the code. Let's move on to network connections. Something else that caught my attention was well, I always wanted to fuzz browsers. I wanted to fuzz browsers and compare the browsers to the command line interpreters, like the ones that I showed at the very beginning. Fuzzing browsers is horrible. It is difficult, it is annoying, they crash, they have a lot of weird ways where they work. But eventually when you got them to work, you can, remember the test case at the very beginning where the summatory was not working very well? In JavaScript, you can do that automatically. You can instruct the browser to try to request a file that is going to be located on the same host, and the fuzzer can then extract what was the output of that operation to try to use it in here. So you don't need to analyze all the outputs. You can extract that information from the fuzzer itself and use that information. In here, I'm using a combination of two things. I'm showing you the example that I showed at the very beginning, and I'm showing you how a piece of software may open a network connection. Sometimes we want to know when someone is opening a network connection. But let's use this on a practical example. JRuby has a remote code execution when it comes to one of their versions, only one of their versions. If you request a canary file that I put in this IP address that executes this, the command ID, this is what's going to happen. There is a load rec file functionality that loads a file with Ruby commands. In here, I'm putting a remote file, but it shouldn't work like that. If you read the documentation, it says load rec file should load a local file. So this is impossible. This cannot work. This isn't Ruby. In JRuby, there are two versions of JRuby. One that is 1.7, that it tries to have all the Ruby versions, and one that is called 9 point something, that only has the latest version. In the 1.7 version, this is the latest version of this branch, you can execute things remotely, even though the documentation says it should be a local file. So you can request a Ruby file and execute it remotely. And if someone embeds this on an installation file of a Ruby program, you can execute code by requesting remote code. So you may embed the exploit or whatever, and then do something about it. Again, the first thing that I executed was not the command execution. I had a canary token something to detect the network connection, and I also detected how it was opening the network connection. Once you get that hint of what do you want to do, you may want to try to see how that's going to be exploitable. Let's move on to the latest example of how you can do things. You can read files. The canaries, we use the canaries so far for, well, they can be used for network connections, for code being evaluated, for commands being executed, and for files being read. So if you reference, the fuzzer creates a file named canary file that contains the string canary token file local. If you request a canary file on the web server, the string is going to read canary token file remote. So in here, this is the analytic function for the canary tokens files local. And this is when you're using Node and you're requiring a JavaScript file. In this case, let me show you how it looks like on a practical example. When you're using Node, when you're using Node, you can change the JavaScript parser. On the left column, you're going to have Chakra Core, which it is made by Microsoft, V8 made by Google. When you're trying to require a non-JavaScript file in Node using Chakra Core, it says invalid character, this doesn't work, forget about it. However, with V8, it's going to show you the first line, and if you're trying to record the etc. shout is being executed by root, you can read the first line. There are a number of first line in different operating systems that are valuable. This shouldn't happen. It is on the, after I presented this, it is on the roadmap to take it off. But you can still try to execute this. So, yeah. Would it be possible? I don't know. There could be a possibility that I made it and it also works. I want to check now. Oh, I don't know if the rest of the people here, there is a single quote is missing in here, so perhaps I made a mistake and it works in both of them. I don't know. That would be more interesting. So the idea is that you can analyze different vulnerabilities. You can read you know when someone is trying to read a file, you know when someone is executing a file. There are a number of things that you can do. And you can expose more vulnerabilities when you're comparing different pieces of software, when you're checking different operating system versions, implementations, or whatever. And something that I believe may be really, really, really interesting in the future is what happens when you have different pieces of software and you have a bug in here, a bug in here, and you have a bug in two different implementations at the same time. One payload may attack multiple pieces of software at a time. And right now, people are only looking for specific payloads that are attacking specific versions of applications. And it would be possible perhaps in the future to start detecting them to affect multiple pieces of software at the same time. Any questions? You can boo. Or thank you very much. You can get a copy of the latest release that I made over there.
Hold on, there's a question.
Yes.
Thank you for the great work. Thanks for the great tool. I think my only question is that in terms of scalability and in terms of, so like I see when you're testing different products like Ruby, Python, etc. Again, like I'll go back to the point of test case generation is like you want to print something. So it could be console.log here or print here, etc. Is there a way kind of to scale this up or a way to generate these test cases for the different inputs? Is this part of the tool? Is this, or do you use this manually?
I believe there let's talk about input generation. When it comes to input generation, I think fuzzers have three parts: the input generation, the fuzzing, and what they're doing with the output. When it comes to the input generation, there are a number of possibilities. When I did the permutations, you have 3 or 4 different types of permutations that you can do, and then you can automatically put input fuzzers to automatically change the fuzzers that you have created with Radamsa and XDiFF. I don't know how to pronounce that one. Okay. So you can grab your 3 poor test cases that I put over there, and you can apply Radamsa and the other one to that one, and you can keep generating constantly input test cases unattended, leave it over there, and may eventually find something. But those are dumb inputs. You can also apply your own smart input over there, if you can. That's why you have the permutations, if you can do something like that. But I believe that what we have seen, even in Hack in the Box, is that sometimes people play a lot of importance to for example, you can grab one day vulnerabilities, grab that as a function, grab that piece of code, grab the places where you want to input values, select that as a function, put certain values of what you want to fuzz that, and then put an input fuzzer, like Radamsa or the other one, and then start building automatically all the test cases and move from there.
All right. Any more questions? No. Okay. We'll go for a break, then come back at 4:30. Thank you very much.
Thank you.